For number five
Hmm.
on the homework, when I take the derivative of the fraction like x to the second over x to the second minus 9, what I do, I probably will, what I do one of those derivative rules, or would I just take it over like 2x over 2x minus, yeah, just 2x. Yeah, what I do quotient rule.
For this two?
5.
Oh, five. Yeah, you have no choice. You have to go through quotient rule. Yeah.
Like, when would there be a time where there's like a fraction well that wouldn't have to be quotient?
Yeah, good question. If it looked like this.
Oh, because you can cancel out the x.
What is it? What is it about this that allows us to avoid quotient rule?
Um,
See if you can discover it.
on the top, it's already, you can do, what's it called?
Factoring?
You can do power rule on the top too, do
Mhm.
I have no clue.
Look at the placement of the denominator versus this denominator.
It's just because that denominator is one term.
There it is. What is it about one term that makes quotient rule avoidable?
So what do you do instead of quotient rule?
You can do power rule. How can I avoid quotient rule for this?
You would just do power rule on top and bottom.
We can split up
yeah.
individual
Makes
fractions
more sense.
and then do power rule. We can't do that if there's
Yeah.
multiple terms below.
Yeah,
I mean, you can do quotient rule here, but we like to avoid quotient rule.
Yeah.
That one, you're forced into it. Give me a second. Let me set up. Let me send in case anyone wants to join online.
Goes. That's student council. You're in student council. 740. Probably would be on the front. So that total, don't have more.
Morning. Okay, let's do this. First of all, any individual questions? Okay, let's do worksheet 4 then. Okay, so you have a function. Does Rolle's theorem apply? So walk through that. Okay, so with Rolle's theorem, first off, any theorem, there are some conditions attached to it, right? What are the conditions that we need to make sure we take care of, or that we make sure are good to go before we jump into the rest of the theorem? Continuous and differentiable. All right, so let's now this is a polynomial, we don't have to worry about anything, but here we may have to look at something. Is there something that could get in the way of continuity? Where do we look for continuity issues?
The vertical asymptote.
Yeah, denominator, right? So what is that? What does the denominator show you?
-2.
At -2, right? So there's vertical asymptote. There is a break at the graph. Doesn't mean that every time we see a vertical asymptote that the problem breaks down, but how do we check to see if this is an issue or not for our problem?
See if we get one.
Yeah. Is this vertical asymptote going to interfere with my interval? No. So we're safe. Okay. So if you can make if you can make it past the continuity condition, it'll pass the differentiable condition as well. At least the problems I give you. Maybe when we get to AP review, we can talk about situations where continuous but not differentiable. But right now, let's just get it past that continuity condition, and then you can state the rest of the conditions. So we know issues with continuity, and we're going to have a smooth curve as well. So our function is continuous with brackets, differentiable with parentheses. Okay, I'm looking for this to earn full credit. Okay, next up, Rolle's theorem feels a lot like mean value theorem because here's the formula. Same formula for mean value theorem and Rolle's theorem. So what does this mean, and what is this? What do we want to do to begin with? Yeah, and then do it with that information. And find the what? What is this? Slope. Yeah. So no derivative. Okay, not yet. Let's get our slope information taken care of. So we'll find f of 0. We'll find f of 6. And find the slope between those two endpoints. Okay. So 0. I get 0 minus 0 over 0 plus 2. So 0 over 2 is 0. F of 6. 6 squared minus 6 times 6. That's 36 minus 36. That's 0. 0 over 8 is also 0. So here, my y values are 0. These are the same. What's really going to happen is that my average rate of change, my slope is just going to be change in y over the change in x. What does this give us? It was 0. Okay. So this is what Rolle's theorem needs. Rolle's theorem needs the slope between the endpoints to be 0. Let's make sure that we understand it's the slope between the endpoints, not because that these are y values of 0. Okay. The important thing is that these are the same y values. Right? If it's 2 and 2, my slope is still 0. If it's 6 and 6, my slope is still 0. So I want to make sure that we don't just copy this number down. It's the fact that it's the slope between the endpoints that we get 0. So now we know that there is a place where there's a slope 0, and we're going to make the derivative tell us where that location is. So we took care of this part. We know that this slope is 0. So now we can move on to finding the derivative. And to find the derivative, what rule do we have to go through here? Gaussian rule, yeah. F prime g minus fg prime all over g squared. So here's my function. Okay, f prime times g minus f times g prime all over g squared. So we can expand this out. Make sure you don't ever cancel the numerator. The denominator is usually going to be untouched, and we don't want to mess with the denominator. It's usually just the numerator that we have to worry about. We usually are not able to do anything with the denominator. Combine like terms, 2x squared minus x squared is x squared. 6x is cancel out, so plus 4x minus 12. Okay, so now we have our derivative. We have our slope. We'll set them equal to each other. Now, when we set something equal to 0, and there's a fraction involved, we can also make 0 into a fraction. 0 into a fraction is 0 over what? It's basically 0 over 1. So 0 as a fraction is 0 over 1, and we can cross multiply, and we can solve for x. Anything times 0 is just going to be 0. So we can factor, multiplies to be negative 12, adds it to be 4. 6 and negative 2. Sorry, negative 6. Yeah, hold on. 4x. Yeah, 6 and negative 2. Okay, and then we solve for x. We get x is negative 6 and x equals 2. So now this tells us that on the curve, there are 2 places on this curve where the slope is going to match 0. But are both these locations valid for Rolle's theorem? Where do we want our solutions to live? Needs to live where? Between, yeah, in the interval, right? So which one can we remove? Negative 6, right? Because negative 6 is not between 0 and 6, but 2 is. So there's our solution, 2. Okay, let's look at number 2. Number 2 is a mean value theorem. which is almost identical to Rolle's theorem. The only difference is that this Rolle's theorem needs this piece to end up equaling 0. But mean value theorem, it can be anything. It can be a slope 5, it could be slope 6, it could be slope 10. But Rolle's theorem, this has to be slope 0. Okay, we all see a mean value theorem applies. Again, we have two conditions for mean value theorem. The two conditions are continuity and differentiability. We have to just make sure it passes the first condition. The second condition will go along with it. So we do have an issue, right? The way we look for continuity issues is we look in the denominator. There is a vertical asymptote. Where's the vertical asymptote? At where x equals 0, right? So is this vertical asymptote going to interfere with my interval? It's clearly outside the interval. We're safe. We can make it pass both our conditions. Okay, so we're ready to move on to our formula. So first things first, let's take care of our endpoints, see if we can find the slope between the endpoints. So plug 1/2 and 2 into the function, get our y values, get our order pairs, and then find the slope between the endpoints. Use your calculator for this. So 3/2 times the reciprocal of 1/2 is 3/2 times 2, which gives us 3. Okay, we have our order pairs. Let's find the steepness between these 2 points. That's our average rate of change. This ends up giving us negative 3/2 over 3/2, which is equal to 1. Sorry, negative 1. So we know the slope between the endpoints is negative 1. We're now going to ask the derivative to tell us where on the original function is there a slope of negative 1. But to find the derivative, we could avoid the quotient rule if you want. We can split up into individual fractions, but move ahead with quotient rule, and that's fine. F prime g minus fg prime. All over g squared. Clean this up. So here's our average rate of change. Here's our derivative. We're going to set them equal to each other. Or basically, we're inserting the negative 1 into the f prime location because we know what slope we're targeting. We're just trying to figure out the location of that slope. I'm going to force that -1 into a fraction. That can just cross multiply and solve for x. Get the square root, plus or minus shows up. We have two different locations where the graph is showing a slope of -1, but are both of these valid? Which one do we keep? Just one, yeah. So we call C equals 1. C is the x value solution that we verified. Okay. Next up. Number 3, it says use the second derivative test. So second derivative test is not using the sign lines to find the slope, but sorry, to find the relative max, relative min, but to use the second derivative function. So here's number 3. So when we do a second derivative test, we start off the same way as first derivative test. We find f prime. We set f prime equal to 0. We'll find our critical points. Okay. But from there, the paths will be different. We're not going to do a sign line. We're going to rather plug those candidates into f double prime. So let's find f prime. Set f prime equal to 0. Solve for x. So normally we would do this, right? Normally you would do f prime 0, 6, and try to decide how the arrows are behaving, right? But that would be a first derivative test. Okay, so we're doing it, going down a different path here. We're going to plug these values into f double prime. And then using that result to help us conclude what's happening at these points rather than silence. All right, so here's f double prime. Power rule again. (3x squared minus 12x). Right. Now, do we understand that we're not going to set this equal to 0? Right. If we set that equal to 0, then you're doing test for concavity. That's something else. Right. So we're trying to determine if these are relative max, relative min. We're going to use the second derivative function to help us conclude what's happening there. Right. So we're going to insert these in for the x's. So we'll do f double prime of 0, which is 0 minus 0. Now, this is a strange case here. If your second derivative doesn't give you a positive or negative, then you don't know whether it's concave up or concave down. This is inconclusive. Second derivative test is not going to give us a good result. So inconclusive. Yeah, we didn't talk about that case yesterday. but you won't see it on the quiz. On the quiz, if I ask you to do a second derivative test, you're going to get something that is conclusive. Next up, f double prime of 6. Okay, plug 6 in for x. 3 times 36. That's 108. 6 times 12. That's 72. And we get 36. Okay, so let's talk about this number here. This number is not that important. It's hard to visualize it. It's not a location. It's not a slope. It's concavity. What does this tell us? Right, because this is positive, right? Positive means this is part of a concave up graph. And then my graph is concave up. And I know that this is coming from a place where there's a slope 0. We know there must be a relative minimum here. Right. All right, number 4. Okay, sketch and label a graph with the given characteristics. Part A is a bunch of order pairs, so I'm going to just leave those. We can deal with them when we're ready to graph. Part B, it says that f prime is greater than 0 if x is to the left of -1 and to the right of 2. So that can allow us to create an f prime sign line. If they give us x values, those are going to be critical points. So this means positive slope to the left of -1 and to the right of 2. F prime of x is less than 0. That indicates slope is negative. So slope is negative between -1 and 2. Point of inflection at order pair 1, 2. So that's going to give us a second derivative sign line with an x value of 1. Point of concave down to the left of 1 and concave up to the right of 1. So any questions? Are we able to look at these notations and be able to translate it onto a sign line with the appropriate symbols? All right, so now we're just trying to get this picture onto our graph. Okay, so order pair -1, 4. Order pair 2, -1. Order pair 1, 2. Because they tell us there's a point of inflection at 1, 2. Now, through these points, I'm going to draw 2 graphs here. One, just to kind of help me get a picture. And then second, I'm going to go back and retrace it with more accuracy. But I like to do it twice just because it feels kind of intimidating to do everything all at once. So I'm just going to see if I can get this shape to show up or get the path to show up. I want a relative max at -1. I want a relative min at 2. And I want the graph to go through these points. So I know my graph is going to follow along this path. Okay. Okay. We're not going to veer too far from this path. So this is kind of giving us a blueprint for our graph. Okay, so now around this, we want the graph to be concave down up until 1. So I can retrace it and give it that concave down shape. And then past 1, it's going to turn to a concave up. There's my graph. Any questions at 4? Okay, number 5, find the absolute extrema, max and min. So this is extreme value theorem. Extreme value theorem only has one condition. What's that one condition? Function needs to be what? Continuous, yeah, just continuity. Okay. No differentiability with extreme value theorem. You only have differentiable and continuous if it's Rolle's or mean value theorem. Right, we do want to look at the denominator. Denominator could cause some issues, but if I try to set the denominator equal to 0, I'm not going to get a real number here. I'll get x squared equals -4. Square root of -4 is imaginary. Imaginary is not something I would worry about. So there's no real number that can cause my denominator to be 0. So there's no vertical asymptote. There are no breaks. My function is continuous. But with extreme value theorem, we're trying to find the highest and lowest points on the graph. We know endpoints are candidates, so eventually we're going to plug the endpoints into the function. But we also need to find critical points as well, because critical points, slope zeros, could also end up being max and mins, highest or lowest points on the graph. So we got to go to our derivative, set the derivative equal to 0, and find our critical points. So to do that, we have to go through quotient rule. So f prime g minus fg prime all over g squared. Okay, it's going to clean up all the way to 16x all over x squared plus 4 squared. Okay, we talked about how once we find our derivative, we have to set both the numerator and denominator go to 0, right? Those are places that we look for critical points. Your denominator is not going to produce anything because if you try to set x squared plus 4 equal to 0, you'll get x squared equals -4. I can't get square root of negative numbers, so no, imaginary numbers, nothing to worry about, and then denominator. The numerator, if I set the numerator equal to 0, I will get a critical point. What do I get? X equals what? Divide by 16, x equals 0. Okay. Is 0 a valid critical value? Yes, right. It sits between -4 and 4. So how many points are we going to test for max and mins? 3. You have one critical point. You have 2 endpoints. And how do we test them? How do we determine if these are relative? Oh, sorry, if these are absolute max or mins? Which one? The original, yeah, the original will give you your y values. Okay. So we'll plug -4 into the function, plug 4 into the function, plug 0 into the function. And then you compare their y values. Your highest y value is your absolute max. Your lowest y value is your absolute min. Here, there's a tie for highest y value, so it'll be 3/5. The lowest y value is -1, just the y value. Okay, we'll do more review in class. We will start our next section, but the next section is kind of a putting everything together. Okay, obviously this next section won't be on the quiz, but it'll still be useful, and we use second half of class to continue reviewing. Okay. Let me know if you have any questions.